Hi, welcome back. So in part two of It's a Small World, we're going to be dealing with some units that are slightly larger than atoms, molecules, and compounds. But before I define both those terms, just a disclaimer, if you haven't watched part one yet, some of the terms I'm going to use in this video may seem unfamiliar to you, so make sure you watch part one first. Anyways, back to molecules and compounds. Well, molecules are simply a group of atoms that are bonded together. So let's take oxygen gas, for example. There's one oxygen atom right here and another oxygen atom, and they're bonded together. These two lines signify a bond. Therefore, it is a molecule because, it's two different atoms bonded together. Hence, it's a group of atoms bonded together. It's as simple as that. So oxygen gas is a molecule. Meanwhile, a compound is a substance that consists of two or more different elements bonded together in a fixed ratio. So oxygen gas would not be a compound because there's only one element in this molecule, and that's oxygen. However, water, which is shown right here in this diagram, is both a molecule and a compound. How's that possible? Well, it fits the criteria to be a molecule because it is a group of atoms that are bonded together. There are three different atoms. And it's also a compound because there are two or more different elements contained in this molecule because you have oxygen and hydrogen. Therefore, water is both a molecule and a compound, while oxygen gas is only a molecule. Now, I'm sure you heard me repeat the word bond a bunch of times in the last minute or so, and that's because the formation of chemical bonds is what leads to the formation of both molecules and compounds. For me to elaborate on that, we first have to head over to the atom structure diagram that I showed you in part one. In part one, I explained what electrons, protons, and neutrons were. Just as a refresher, electrons are negatively charged, protons are positively charged, and neutrons are neutrally charged. Both protons and neutrons are located in the center of the atom, called the nucleus. But I never told you what the rings that surround the nucleus were. Well, these rings, since they store the electrons, as you can see in this diagram, are called electron shells. So here we have the atom structure diagrams of hydrogen, oxygen, and sodium. As you can see, hydrogen has only one electron shell, while oxygen has two electron shells, and sodium has three electron shells. Why do they have a different number of electron shells, you may ask? Well, the number of electron shells an atom has solely depends on the number of electrons it has. So hydrogen, for example, has only one electron. Therefore, it needs only one electron shell to store that one electron because the first electron shell can hold up to two electrons. Hence, helium, which is not shown on the screen, has two electrons. So helium also only has one electron shell because that first electron shell can store both of its electrons. Next, we have oxygen, which, as I just said, has two electron shells. And that's because oxygen has 8 electrons. So though the first electron shell holds its first 2 electrons, it still has 6 electrons left over, which are stored in the second electron shell. As written right over here, the second electron shell can hold up to 8 electrons. And that's why sodium, which has 11 electrons, needs a third electron shell. Because think about it. The first electron shell will hold its first 2 electrons, so now it has 9 electrons left. The second electron shell can hold up to 8 electrons, so 9 minus 8 is 1. It still has 1 electron left over, thus it needs that third electron shell to hold that last electron right here. So let's practice with this concept. Carbon has 6 electrons. How many electron shells does it have? I'll give you a few seconds, but if you need more time, feel free to pause the video. If you said that carbon has 2 electron shells, you were correct, because its first 2 electrons would be stored in its first electron shell, and then its last 4 electrons would be stored in its second electron shell. Though obviously all of the electron shells in an atom are super important, the outermost electron shell of an atom is of utmost importance because it determines the chemical reactivity of the atom. The outermost electron shell is called the valence shell of an atom, and the electrons that are contained in this valence electron shell are called valence electrons. So let's look at fluorine, for example. Fluorine has two electron shells. Therefore, its outermost electron shell is its second electron shell, and therefore, its second electron shell is its valence shell. Fluorine also has 9 electrons. It has 2 in its first shell and 7 in its second electron shell, which, as I just said, is its valence shell. Therefore, it is said to have 7 valence electrons. However, it may surprise you that its valence is not 7. Its valence is actually 1. And that's because you have to understand that an atom's valence and the number of valence electrons it has are very different. An atom's valence is simply how many more electrons it needs to fill up its valence shell. What does that mean? Well, you may remember that I had told you that the first electron shell can hold up to 2 electrons, the second electron shell can hold up to 8 electrons, and the third electron shell can hold up to 8 electrons. Since fluorine's second electron shell is its valence shell, it needs 8 valence electrons to completely fill up its valence shell. It already has 7 of these valence electrons. Therefore, it needs only 1 more valence electron to fill up its valence shell. Therefore, it is said to have a valence of 1. But why does this matter? Well, in order for an atom to be chemically stable, it needs to have a full valence shell. And atoms strive to be chemically stable through a variety of methods. The first method that atoms use to complete their valence shell and thus become chemically stable is sharing electrons with other atoms. So let's take a look at an example of this. So here we have 1 oxygen atom and 2 hydrogen atoms. The oxygen has 8 electrons, which are in light green, and 2 of them are in its first electron shell, and 6 of them are in its second electron shell. The second electron shell is oxygen's valence shell. Thus, oxygen has 6 valence electrons. It needs 2 more valence electrons to become chemically stable, since, as you may remember, the second electron shell can hold up to 8 electrons. Meanwhile, hydrogen atom has 1 electron, which is in dark green, and 1 electron shell. Because it only has 1 electron shell, hydrogen's first electron shell is also its valence shell. Therefore, hydrogen only needs 1 more valence electron to become chemically stable. This is because the second electron shell can only hold up to 2 electrons. Therefore, each of these hydrogen atoms need 1 more valence electron to become chemically stable. So just to recap, oxygen needs 2 more valence electrons, and each hydrogen atom needs 1 more valence electron. So how do these 3 atoms become chemically stable? Well, they need to help each other out by sharing their electrons. So what's going to happen is that each of the hydrogen atoms are going to approach the oxygen atom. The hydrogen atom, both of them, will each share 1 of their electrons, their only electron, with the oxygen atom. And the oxygen atom will be fair, and it will share 1 of its 6 valence electrons with each of the hydrogen atoms. So oxygen is sharing 2 electrons, 1 with each hydrogen atom, and each hydrogen atom is sharing their only valence electron with the oxygen atom. So what does this do? Well, as you can see, now the hydrogen atom has 2 valence electrons because the oxygen is sharing 1 of its electrons with each of the hydrogen atoms, giving them 2. Therefore, each of the hydrogen atoms are now chemically stable. Meanwhile, the oxygen atom now has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, meaning that the oxygen atom is also chemically stable. When 2 atoms share electrons with each other, they bond. And the bond that they form by sharing electrons is called a covalent bond. So right here, this hydrogen atom is forming a covalent bond with oxygen, while this oxygen atom is also forming a covalent bond with the other hydrogen atom. When 2 hydrogen atoms and 1 oxygen atom covalently bond as shown in this diagram, a compound called H2O forms, better known as water. Additionally, there are two different types of covalent bonds, polar covalent bonds and non-polar covalent bonds. Distinguishing between the two different types of covalent bonds really just comes down to the electronegativities of the elements involved in the covalent bond. What's electronegativity, you may be wondering? Well, electronegativity is simply the attraction a given atom has towards the electrons in a covalent bond. Depending on the electronegativities of the atoms involved in a covalent bond, the electrons shared in a covalent bond could be shared unequally, meaning that the electrons could spend more time near the nucleus of one atom than the other. Based on my experience in AP Biology last year, you really only need to know about the electronegativities of 4 elements, and these are oxygen, nitrogen, hydrogen, and carbon. Oxygen and nitrogen are highly electronegative, meaning that they are highly attracted to the electrons of a covalent bond. Meanwhile, hydrogen and carbon are not very electronegative at all, meaning that they don't have that much attraction towards the electrons in a covalent bond. So now let's go back to our water molecule example and see how electronegativity plays a role in the covalent bond shown right here. Well, what's going to happen is that these shared electrons are going to spend more time near the nucleus of oxygen than hydrogen. They're going to be shared unequally because oxygen is highly electronegative, while hydrogen is not very electronegative at all. Therefore, these electrons are not shared equally. They're shared unequally, and oxygen gets the larger share. When two elements that have very, very different electronegativities form a covalent bond with one another, it's called a polar covalent bond. So oxygen and hydrogen is an example of this because oxygen is highly electronegative, while hydrogen is not very electronegative at all. If nitrogen and hydrogen were to form a covalent bond with one another, because nitrogen is highly electronegative and hydrogen is not electronegative at all, it would be a polar covalent bond. Another example, oxygen and carbon. That would be a polar covalent bond because, yet again, oxygen is highly electronegative while carbon is not electronegative really much at all. Now, what's the effect of a polar covalent bond? Well, it's going to cause the charges of the atoms involved to slightly change. And this is because electrons are negatively charged. So like the unequal sharing of electrons is going to change the charges of these atoms. Because normally, if this oxygen atom was alone and not bonded to these hydrogen atoms through a polar covalent bond, this oxygen atom would have 8 protons, 8 electrons. 8 minus 8 equals 0, thus it has a net neutral charge. However, because it now is partially gaining an electron because, even though it's shared, it's getting to spend more time with the shared electrons than hydrogen is. It's kind of like it's partially gaining negative charge. Therefore, oxygen now has a partial negative charge. Meanwhile, hydrogen is partially losing an electron. And normally, if hydrogen was not bonded to oxygen, it had 1 proton, 1 electron, 1 minus 1 equals 0. But because it's partially losing an electron by sharing its electron with oxygen, it now has a partial positive charge. And this is going to be the case for both hydrogen atoms shown right here. So now let's look at a different scenario where we have 1 carbon atom covalently bound to 4 hydrogen atoms. Here are the covalent bonds right here, right here, right here, right here. Remember that both carbon and hydrogen have very, very similar electronegativities because both their electronegativities are low, very low. Hence, these shared electrons will not spend more time near hydrogen's nucleus nor carbon's nucleus. Rather, these electrons will actually be shared equally between carbon and hydrogen because neither of them is more electronegative than the other. When a covalent bond is formed between 2 elements that have very similar electronegativities, it's called a non-polar covalent bond. And that's the case when carbon covalently binds to hydrogen, like it is in this diagram. So that's all for part 2 of It's a Small World. In the final part 3, I'm going to be unraveling the science behind ionic bonds and weak attractions like hydrogen bonds and van der Waals interactions. Hope that helped, and thank you so much for watching.